In the past few videos, we've been looking at what we call linear least squares regression. And so we learned how to fit a line, for example, across a set of points that we're given. And we've referred to this term linear model a couple of times, and we just use the term loosely. So this video, in this video, we're going to define more carefully what we mean by a linear model. So the setup of this problem is the same as before. We're given some data. We call this data f of k here, with k equals 1, 2, 3, because in this specific example, we're going to just look at 3 samples, right? So at index 1, we have value for f of 1. At index 2, we have value f of 2. At index 3, we have f of 3. So this is the data that we're given, and we can look at the data just as a list given like this, or we can put this list in the form of a vector, where f1 goes the first element, f2 is the second element, f3 is the third element. Again, just a name for it. And then we're looking for a model, which we call v, right? And again, we can evaluate the model at the same index points as the data. And we can also look at this model as another vector, right? And in the specific example that we just saw in the video before this one, we looked at this model, right, where we essentially have the equation of a line. So in other words, we're looking for the line that kind of passes closest to all these 3 points. So that was the purpose. How do we define how close a line passes to points? And we sum the square differences. And then how do we fit this model? We solve for the minimum of a function. We take the gradient to the set of derivatives to 0, evaluate the set of derivatives, set them to 0, and find the points, meaning the coordinates a and b, that minimize this error. So this was the topic of the last video. And in this video, we're going to take a closer look of what do we mean by a model like this. So if we take this definition here and we expand, well, we plug in what we know for each value, and this is what we're going to do here. For v evaluated at coordinate 1, we plug in 1 for k, so this is a times 1, and we also add b, so I also say b times 1 here, just to be pedantic for a second. We do the same thing for the second coordinate, right? We just plug in k equals 2 for there, so a times 2 plus b, so plus b times 1 is plus b, the same. Same thing for the third coordinate, so we have a times 3 plus b times 1. So we can look at these 2 terms, right? You can notice that each of these elements here has 2 terms, term 1 and term 2. So we can separate, look at the term by term, and we can realize that this by itself is a vector. And in fact, I can take the a out of this vector. So here I have a, and I took only the terms 1, 2, 3 for the vector. Same thing for this term here, right? I consider this as another vector. I can take the b out. This is what I've done, separated the b and selected the vector 1, 1, 1. So our model, and furthermore, we can call this vector here 1, 2, 3. I call this vector phi1. It's just a name I'm giving for it. Likewise, I'm calling this vector of 1, 1, 1 vector phi2. So our model can now be interpreted as the linear combination of 2 vectors, phi1 and phi2. The coefficients of this linear combination are given by a and b. And the whole problem that we solved in the last video can be restated as sort of finding the values of a and b such that the vector produced when I plug in this linear combination here, this vector is closest to the input data that I'm given, the data f. So it's a geometric interpretation of what's going on. So let's look at this more closely. We can, because these vectors are in 3 dimensions, right? We have f has 3 coordinates, and so does phi1 and phi2. I can draw these vectors on a 3-dimensional axis. The drawing is not so pretty because it's hard to draw things in 3 dimensions. But here is the vector f. And you can see, right? So you can trace the value, the third coordinate is roughly 2.5 or so, which is what we wrote over here, right? This is the third coordinate for that. The first coordinate is 1, so we have, and the second coordinate is roughly 3, right? So this is, here we have roughly 1 and roughly 3 for those coordinates. So that's our vector f. We can do the same thing for phi1, right? Phi1 is the coordinate 1, 2, 3. So we have here 1, 2, and all the way up 3. So this is our vector phi1. Likewise, phi2 is given here, 1, 1, 1. So we have here 1, 1, and then we go up 1. So this is our vector phi2. So we're trying to add these two vectors, phi1 and phi2, and we're trying to multiply vector phi1 and phi2 by some constants in such a way that this vector f here will be this linear combination will be closest to this point f. So now this is a tricky thing to do because it involves drawing in 3 dimensions, and I'm not very good at it. But you can view the set of all possible linear combinations of phi1 and phi2 as sort of this plane here that sits on this set of coordinates. And the point within this set of linear combinations from phi1 and phi2, right, we cannot get exactly all the way back here. That would mean that we are perfectly, that our line would pass perfectly through all of these points, right? And you can see these points are organized such that they don't pass through one common line. So a perfect finding values of a and b such that this vector here is exactly equal to f, in other words, a perfect representation, is not possible. Perhaps it could be possible if we had phi1, phi2, and another phi3 somewhere. Then, depending on what the phi3 was, that could be the case, but it wouldn't be possible in this case. So we're looking for the point within the plane that is composed by this reconstruction of the addition from phi1 and phi2. So this is going to be our VAB vector. Right? So that's one way to interpret what's going on. And you can see that the model is giving us the model I selected, right? This is something that we set a priori. We select the model if we want a line, and we're going to do next a quadratic function. The model itself gives us these vectors phi1 and phi2, and then when we're trying to do a least squares approximation, we're simply searching for the coefficients of this linear combination that give me a vector that is closest to f, and the geometric picture, the interpretation of all that's going on is here. So let's go to the question, what does a linear model specifically mean? So let's look at another example. What if our model contained 3 terms, a, b, and c for k, but now it involved a quadratic function on k instead? Right? Just so this is, now let's look at this model. Going back to our original plot, this means that we're trying to fit a quadratic function here. In this case, we would have to find the right coefficients a, b, and c such that the quadratic function that this draws fits perfectly within this set of points. And in fact, from the lectures on interpolation that we just did, you can figure out that this would indeed be possible to have a quadratic that perfectly passes through 3 points. We in fact did it in a couple of different ways. But what I want to do here is realize is once again do this decomposition right, where we have our vector v a, b, c can be written as these three components, a, b, c, evaluated at the first coordinate, v, a, b, c, evaluated at second coordinate, v, a, b, c, evaluated at third coordinate. So that's our vector. And once again, we can plug in what we know for the model. In this case, we're looking at that specific model. So let's plug that in. So this is going to be, the first term is going to be ak squared plus bk plus c. Oops, sorry, I should have been plugging this in, so let me erase this. So this is going to be a1 squared, so I'll just write a1, right, plus b1 plus c, and again I'll write times 1. The second term will be a, now 2 squared, oops, 2 squared is 4, right, so 4 plus b times 2 plus c times 1. And the third component will be a, 3 squared will be a9 plus b times 3 plus c times 1. So this is, in fact, our vector. And once again, I can look at this as a sum of 3 separate vectors. And I'm going to do the same thing that we did above. So we're going to separate the coefficients from the vector themselves. So this is a 4, 9 plus b 1, 2, 3 plus c 1, 1, 1. And so, and this is again our vector, our model vector, a, b, c. And once again, I'm going to make substitutions here. I'm going to call this phi1, and I'm going to call this phi2, and I'm going to call this one phi3. So this is going to be equal to a times vector phi1 plus b times vector phi2 plus c times vector phi3. Right? Or in other words, when we have our model, let's say our model is given as VABC of k, and that's going to be AK squared plus BK plus C. We can also write it as A phi 1 of k plus B phi 2 of k plus C phi 3 of k, and in this case phi 1 of k will be equal to k squared, phi 2 of k will be equal to k, phi 3 of k will be equal to 1. So this can be used to represent this technique of, looking at this model vectors, the vectors that come from our model, can be used to write any linear system. We just change any linear model. We just change the definition of the vectors. But the bottom line is that once you define these vectors, they're coming from your model. The model is linear in the sense that the parameters you're seeking, A, B, and C, right? Well, again, we're seeking the parameters that define the quadratic function that best passes through the problem we have. Can be a quadratic function, can be a cubic function, can be a fourth order polynomial, and so on. They're all linear models in that, of course, a quadratic function is not a linear function. Nonetheless, as a function of the parameters that we're seeking, not of k, not of the independent variable, the original independent variables, but the parameters that we're seeking, they're all linear because the parameters that we're seeking appear linearly. There's no a squared, there's no b sine of b, there is no square root of c or anything like that. Right? So a general way to write a linear model is we can write now our model, let's say, as a function of some vector of coefficient c. So I'm going to lump these parameters a, b, and c into a vector c. So this vector will contain a, b, and c. So the general way to write this linear model, of course, this will be a function of k, will be sum over k equals 1 through, let's say, m c k times phi k. Apologies, I should have used a different variable here, so let me go back. Let's use a p here. 1 through m c of p phi p of k. And yet another, so and in this case, right, our c for this particular example, our c vector was the vector of a, b, and c from these coordinates here in our model. So this is just a generic way to write a linear model. And as you can see, the coefficients that we see here, they appear linearly. There is no c squared, there's nothing nonlinear going on those coefficients. And one more thing that I want to write, you can actually write this, right? So if you write these vectors here and put them as separate columns in one matrix. So let's define this matrix B, which I'll write to be, on the first column I'll put vector 1, and the second column I'll put vector 2, and in the third column I put vector 3. Then, with this definition, I can write actually my vector v, again is parameterized by some coefficients vector c, as the matrix B times my vector c. And this is a more summarized version of a linear model. Anytime your model for, again, the data that you're seeking, and here's our problem again, find a representation of this data f, and the model is going to be, in this case we started with a line, and then we wrote that the line can be the addition of two vectors. So it's the quadratic function, so there can be the addition of three vectors, right? So here are the three vectors we defined. All of this can be written as a matrix B, and once again the matrix is defined over here, times a vector of unknown coefficients. Anytime your model can be written this way, and you can have three vectors, you can have four vectors. These vectors can have, three values for k as we have, or can have 10 or 1,000. This is a generic way to write. Anytime your model can be written as a matrix times the vector of coefficients that you're seeking, this is what we call a linear model.